Hello everyone, my name is Walid Balid. Welcome to session number 5 of the printed circuit board design principle and practices. In session number 4, we went over the PCB design and manufacturing process, and then we introduced the schematic and layout design workflows in Altium Designer. And we will revisit the workflow later, where we will design 4-layer PCB following the schematic and layout workflow discussed in session 4. But before we do that, we need to learn how to create component libraries, and also we need to dive into signal integrity concepts and introduce PCB design best practices. So for now, we need to do the second part of session number 4, where we started with a stable multi-vibrator design using through-hole components only. Today we will redesign the same board but using surface mount components only. Now, this is the layout for our board, and as we can see, we have 9 green LEDs, we have also 9 red LEDs, and we have a power interface in here. We can use micro USB connector with micro USB cable, so you can use the same your cell phone charger to power up this circuit. And here is an examples of these surface mount LEDs. These are the through-hole LEDs, and you can compare it to the surface mount LEDs. They come in different sizes. Even for the through-hole part LEDs, these are 3 millimeters, for instance. These are standard, and there is a 5 millimeter, 7 millimeter, and 10 millimeter. And this is the diameter of the tip of the LED. Now, for the surface mount LEDs, some of them follow the same coding or size coding for resistors and capacitors. They come as 0603, for instance, or 0805, and some of them has a different size. So these are different sizes for the LEDs, and we are going to use 0603, which is this one today, in modifying the circuit from through-hole part to surface mount. And then again, I always remind you to learn Altium Designer as you go. Whenever you got a question or you are hovering over a command, you don't know how to use it, just move the cursor over that command or panel or the dialog and hit F1 on your keyboard, and Altium Designer will take you directly to the documentation where you can find comprehensive information about whatever was under the cursor. And also, while you are running a command, for instance, you selected a wire or a route, and then you can click Shift F1 and you will display a list of the command shortcuts. Now let's switch to Altium Designer. This is the schematic we created in session number 4, and all these are through-hole part components, and we only need to replace these with surface mount components, and we will do that in a second. But before we do that, I received a couple questions about the 3D models on the layout specifically. So you know how you can switch between the 2D model, 2D view and the 3D view. So in here, so some of them ask how we can copy this 3D model for the resistor into the rest. So they try to click on it and copy, and you get this. So it's snapshot. This is, you are not copying the 3D model. In order to do that, you either add place a 3D model, again, the same resistor, same 3D model, or in order to copy that, you need to switch to the 2D model, and you need to go and view the mechanical layer where you have the 3D model placed on, and then in this case you just click on the 3D model. If this is the 3D model, right click on it, and now you select the center of it or the snap point, and then now you can paste. This is the 3D model. Now you can base it over the second component and third component and so on, and try to align it. So let's place it here. Let's switch to the 3D model, and that's it. This is how you can copy a 3D model. So you need to align it to remove the collision. You have a collision in here. This can be clear, it's not a problem. But this is how you copy it. Now, the second question was how, if we couldn't find a component, can we create that? Yes, you can do that. If you have some experience with SolidWorks, you can go and do it in SolidWorks, or if you have a component, you can modify it to fit the component you have, or you can do it in Altium Designer by going to place extruded 3D body in here. So you can count the extruded 3D bodies to create the component. For instance, the capacitor. Let's create a body for this capacitors. This is the capacitors we need to place, as you can see in here. It has around 7 millimeter, and this is around 300 mil by 75 mil in diameter. So basically, we can create that using extruded components. Now to do that, go to place extruded 3D body, and you need to hit on tab to go into the properties. So the generic is basically when you choose an external 3D model. Extruded, it's different type, but we need a cylindric or cylinder. So it's cap, it's cylinder. Go back to the properties. Now the height for this one is 300 mil, or you can put 7.5 millimeter, and the software automatically convert that to mil, but it's 300 mil or 7.5 millimeter. So the radius for this is 75 mil. I have this information from the datasheet of the component, and the standoff height is just the height between the cylinder you are going to create and the top surface of the PCB. It has around 7 mil height. So now you can also change the color. We can change it later. Let's put this component. Now if we zoom in, you see the component in here. So let's place it in here. And this is the component we have. So we can take a look at it. It's cylinder 0. And what we can do now, we can change the color for this component. From here, let's say it's black, and let's increase the standoff height a little bit. And here is the component. Let's change it to here, properties. Let's go with this color. Okay, so this is the cap. We have created a 3D model for the component in an easy way. Now we need to change all the components into surface mount components in here and modify the layout. But before we do that, we need to make a copy of this project because we need to keep it. And you have two ways to do that. The first one is basically you can go to the project folder and create a folder called a stable SMD and copy these files into that folder. Now the other one is basically you can come in here, file, save project as, and you can create a folder and save the project inside this folder, SMD. But now I need you to notice what will happen into these icons for the schematic and the PCB. When I click on save, the icon will change into a reference or a shortcut, similar to a shortcut, instead of the original one, as we can see in here. This means that there are projects in a folder, but these files are in different folder. They are still in the original folder. Now, any change you make to these files will reflect into the original files. Basically, you are changing the original project. So you need to be very careful about this point. Now, how we can solve this? In this case, you need to create a copy of this file. As you can see, the link point into the original folder where the through-hole project is. So you need also to save as or create a copy of this into the surface mount project folder. Now the icon has changed, as you can see, because now it's just pulled from the same project folder, and now it's totally a separate file. You will not change anything to the original file or original project. So save as, let's create a copy of this also in the SMD folder, and see the icon will change. Now these two files are in the new folder we created for the new project as well, and you can make any changes now to this file. Now let's start by changing this resistor. We need 1.2 kilo ohm resistor, and we need to change all these resistors. So you can select all these resistors, but you might select wires and nets and different things. Now if you click on the free area, you can go to the properties and you can filter out all the object and keep only the parts or components, these components. Now if you select here, basically you are only selecting components, nothing else. So we need to replace all these resistors in here and all these resistors in here as well. So all these are 1.2 kilo ohm. So we can go to the manufacturer part search as we did in the first project. So we need res SMD and 1.2 kilo ohm, and we need the size to be 0402. This is the size we need to be. So here we can see a lot of components. Let's maximize this panel, and once you see this symbol next to the component, that means this component has a model. You can use it right away. The model I mean by that is the schematic and the layout. So this is the schematic, this is the parametric information about the component, this is the size of the component, and so on. So this is the schematic symbol. The 3D model, you can click on the 2D and you will see the 2D model. In addition to that, you can see also various sizes based on the IBC standard for density. So you can select the minimum density or low density or maximum density in here. So stay with the normal one, and here you can see the revision. So data sheets and also alternative parts. Here you can replace it with alternative part. So let's go, and here you can see information about the price per unit and the available stock. Now you see the arrow here, down arrow in here. This says you have 28 different component provider for this item or this part number. This is a resistor manufactured by Panasonic, and here are the part providers. So DigiKey, they have it, and this is how many they have. They have 857,000 in stock, and this is the price per resistor based on a specified quantity. And you can see all these in green. The one in red, they don't have it. The stock is 0. As you can see, they are marked with red. So here you can see the supply chain for this component. It's very handy piece of information, and these will update in real time. And every time you generate the bill of material, the bill of material engine will try to pull the updated information in terms of price, available quantity, and also the supplier. So let's use this component. To use it, as we said earlier in last session, you can click here on place, or let's minimize it first, or you right click on it, place, and now you can see how the transparent for the panel is. So you can click on here, and if you need to add another 1, 2, 3, and you add all the components you want. You can copy also and paste instead of adding 9 resistors. So let's try the escape, and you will release the comments. Now this is the part number in here for the component, and if I click on it, I cannot select that. I only can select the component. Remember, we have a filter, and so many people have this mistake. So click on the free area in here, go back to the properties and select all objects. Now we can select the text, because this is, when you hit on this one, this is the text. Now you can replace this part number with the value. So if you click on the resistor, you go to the properties. Now you can hide the comment in here, or you can change the comments to 1K2, or you can hide this and go into the parameters and add a new parameter here and call this value, for instance, value. And here you have 1K2. If you don't want to change the comment in here, so you can view this. It's view now, and you can move it and align it, adjust it next to the components. Now we can replace all these resistors with the one updated instead of going and update each one of them. Or you can select all of them, of course, and change all of them at the same time. So let's just delete them and copy and paste. Now we can do the same thing for the other side, or we can change it later, because we can copy and paste the whole part in here. It's easy once we change the LEDs. Now we need to change these LEDs. I don't know why I have a green LED in here. Looks like I missed this one, but it's fine. So we need to change these LEDs in here. Also, we need to use surface mount LEDs. Let's move this panel in here in the floating mode. So we need red LED SMD, and let's click. So this is the LED 0603. This is the LED we want, and let's take a look. And it's available at different component providers, including DigiKey. Usually I source my components from DigiKey or from Mouser. So Mouser also is very powerful, and the DigiKey also is powerful. So here are the parametric informations. Here is the symbol, the layout we can see in here. This is the 3D model for this LED. And data sheets, right click on it, place. Be careful about the polarity of the LED. We can place it in here. Now let's lock this panel, and we can move the part number. Now we can change this one to red, or you can place this one in vertical way. Just move it and click on space, and this is the designator. We can add also a color to it. So you have a color in here. You can view this color and move this parameter in here. Now let's copy and paste. Okay, and we have another one in here. Let's copy always. Control V. Flip these in X. We click on the X on the keyboard in here. But now, because we moved them, they will go back to the default. The position for these parameters will go back to the default. You can change them. Oh, we have to change. Oh, we have to delete these LEDs to put the green ones in place. So let's take these out, and manufacturer part search. Let's back in here. We need LED SMD, and we need the green. Oops, green LED SMD 0603. You can type all that at the same time. And this one doesn't have a model, and this is from the same provider, so from Worth Electronic. And let's use this one. It's from the same manufacturer or vendor. So let's click on this, down. We are done with this. Dock it. Let's put this one in here, and let's view the color parameter. Here. Can put this in here. Okay. Looks nice. Copy and paste. Very quick. Copy and paste usually in the schematic design is very handy and provide flexibility and will help you to finish your schematic in short amount of time. Now what we need to change is the 10 kilo ohm resistor and the 1 mega ohm resistor. So let's swap these resistors. So we need SMD resistor 10 kilo ohm 0402. Very quick. Also, let's take it from Panasonic place. Let's put it in here. and let's hide the comment and show the value instead of the comment. Where is the value? 10 kilo ohm resistance in here. Now let's copy this to this place, and let's remove this one, mega ohm resistors as well with the surface mount. So again, SMD res, we need 1 meg, and also it's 0402. Let's have it also from Panasonic in here, and this one has a model, and you can move it in here. You can see it's 0402 chip resistor. Now, in order to see the model and the details, you need to expand this a little bit, or you can move it to the floating mode. You can see it. If you still cannot see it, make sure that this command is active. So sometimes it will look like this. So click on this and the information will be available to see. So let's place this component. Let's place it in here. Let's move this. And now again, let's 1 mega ohm. Let's hide. And we need this one. Let's place it here. Can put this one in here. Control C, Control V, and they are in place. Now let's change the 220 nanofarad caps in here, and we can use ceramic caps. Let's move this here. So ceramic cap SMD microfarad and 0402. So this one 10 volt, and we have 5 volt. Let's go with the 16 volt for the tolerance. We are not discussing now the best design practice from a circuit point of view. We are talking about PCB design. So we'll go with the 16 volt in here. So let's hide some of this comment, and we don't need this. We can change the comment, or you can keep the comment and go to the parameter and view the value for this. Usually, in addition to the value, in most of my designs, I put the voltage as well, because usually I do high voltage circuit design, and this will include also low voltage and high voltage, and I need to make sure that the high voltage side will have high voltage rated caps and low voltage side using low voltage rated caps. So I don't want to like copy and paste in wrongly from the low voltage to the high voltage, and if you apply high voltage on low voltage rated cap, it will blow up. So we don't want to do that. So I keep the voltage parameter on all the time, just to have an insight into the cap rated voltage. Now what left to change is these transistors and the diodes, and also we need to change this cap. We don't want to forget this guy in here. Let's change it, and this connector as well. We are gonna use okay, looks like we closed the panel. We can bring it back again. We need to micro USB connector SMD. Let's get one. So this is not this one. This has a shell. This is a surface mount. You can see the shell. No, this is not good one. Let's go with this one. Let's find one that is okay. This one looks. Let's wait for the 3D model to come up, and these are the shells. Heroes. Now this one in red, this is end of life. Don't use something end of life. So usually I like something from Worth Electronics. They have a very robust models. So this one looks good, and you have mechanical relief, stress relief in here. So using through hole, this will be very helpful to reduce the stress on the surface mount connectors on the or surface mount pins. So let's use this one. So now we need to flip it, use X and place it in here. Let's close it, and we need also one in. Let's change this one. Let's see if there is a surface mount version of it. Place. We need one, and also we need to change a transistor. And this one 2N. There is no surface mount version of this. This is old style transistor, but let's take a look. If not, we can replace it with 3904. Let's see if there is any surface mount. No, of course not. Oh, there is something similar, but what we need is we need transistor SMD, and we need 0.2 amp. Let's see. So this one is very good one. So it has nice transient frequency and switching frequency as well, and enough power for the switch. So we can use this one very quick. Usually you have to go through the data sheet and make sure that you are selecting the right transistor, but now we are just learning PCB design. So we need also power transistor. Let's search for NPN transistor, 1 amp surface mount, and we can pick any one just for sake of training. So this one, 500 milliwatt, 1 amp. Okay, this one can work. And let's place it in here, and also X to flip it in here. And I think we had all the components. So let's change these two diodes with the surface mount one we just selected. And we have this one in here. Copy this one, Control V X to flip it here. We need to change these two. This is the transistor we picked. And we can move this one in here. Control C, Control V X, it will flip. And we can move so this one here. The Q designator, and we need to change this. Can change it with that. And so the reason why you see this junction in here, because you have two pins in here, and this is indicated in here 2,4. That's when you have two pins, because this model, this transistor has 4-pin model. So pin number 4 and pin number 2 are the collector. So if you go to the view footprint in here, so you can see 1, 2, 3, 4. So pin number 2 and 4, these are aligned, they are the collector where your load is connected. So that's why you see the junction is not wrong. So in here, oops, X, let's connect this. Same case, you see the junction in here. So let's move this in here. And designator. Okay. Now this is an extra, we don't need it. I think we have changed everything. Oh, we need to connect the USB connector. Now for the power supply on the USB connector, if you want to get the power supply, number 1 is the 5 volt and number 5 is the ground. So this is what you need to connect for now. You will get the power from the USB. Of course, you need in real design, you need to protect the USB from overcurrent, from short circuit, and etc. When you do robust design. But for now, we are not doing that because it's just to practice on a simple circuit board. Now everything is done. Remember, what would be the next step? The next step is to annotate schematic. Now some components might have previous annotation, So what you can do to start the annotation from the beginning, you can go to Tool, Annotate, Reset Schematic Designators, and now everything will go into the reset state. Now everything will have a question mark, it needs to be annotated again. So we can go Tools, Annotation, Annotate Schematic, update the list. You have 50 changes, which makes sense because you have 50 components on this board. And now you can validate these changes, and you can see the old and the new name for every single component, and you can execute these changes. Now it's very important to check if there is any error, but we don't have any error here. So now we can see that all of them are 1, 2, all the way to 10, 11, 12, all the way to 22, and we start with LED 1 to all the way to LED 18. So the schematic is good. We can save, and we can now compile in here to make sure that we don't have any error. We go to the messages, compile successfully, no errors found, and it's ready. Now this is our old PCB. We just made a copy of it. Now let's go back to the 2D view, and this is the old component placement, and they are still not updated. Now you need to go to the schematic and click on design. Let me put them next side by side so you see what's going on. Okay, window, vertically. Okay, so let's click on design, update PCB document. Now usually I prefer to unroute these because we have made major changes to the components and everything. You need to reroute the board anyway, so I prefer to unroute everything, even the polygon. We can remove it, and then it's easier to move the components and rearrange them. But before we do unroute, let's try to send the component and change everything and see what will happen, and then we can go back and delete everything and also regenerate the components. So design, click on schematic in here, design, update, and now you will get this message: failed to match 50 of 50 components, because you have changed the footprint, schematic designator, and component ID for all these components, and they will not be matched. There is no identical component for any one of the schematic or the layout. So what you can do, always select automatic create component link. Now you have created 50 links. You need to match these manually. Don't match anything manually. Leave it up to the Altium wizard to make these changes, and you need to verify. Now validate changes. Now checked. Now let's execute changes. Now Altium Designer will, or the ECU engineering change order, will remove the through-hole parts and put the new surface mount parts in place. Now let's see if there is any errors. No errors, which is good. If you want to make a report for these changes, you can do that in here, and you generate a report. So we can see here, let's take a look at the 3D view. You can see these are the new LEDs. Now why they are in place? Because they have the same designator. So LED 1, LED 1 through hole part, LED 1 replaced LED 1 through hole part. So the component replaced the old one in the center of the old one. So the center of the new component aligned with the center of the old parts of, or the snap in position. So you can see you have the LEDs in here, resistors in here. Remember, we had through-hole resistors in here and also in here. Let's remove this 3D model because this were the old one. Look how much the size is different now. So resistors, transistors. So these are, this one and this one are the switching transistor. These are the load transistors in here. and we have the diodes. They are small, and now we can reduce the size of this board significantly. Now, again, as I said, you need to unroute everything before you start porting the component, but you can unroute even after transferring the components. Let's go back to the 2D model. So you select on the top layer, you click on the polygon, you click on delete, it will be deleted. Select the bottom layer, click on the polygon. We are gonna recreate this polygon, and you can create that. Now, if you click on R on the keyboard, it's it's unroute. So you have unroute all, and they will be unrouted. This one, okay, you can, if you select this wire and click on tab, it will select the rest of the trace as well. You can delete this one. For instance, this one, tab, and it will select the rest of it. You can delete that. So let's move this connector, and now we need to position all these components and start routing as we did in the through-hole parts. So let's close the schematic because they are already positioned in a nice way, because they only swapped the place of the through-hole part components. But you can see these LEDs are flipped, so you need to rotate this 180 degree. Now it's clear, because if you try to route this, it's on the other side, and this is not good. You need to reduce connection crossing as much as you can do that. So you can click on space and you can rotate all these components. Now let's see. Let's merge and make the screen big, and we can start. Let's save everything, and we can start route. We can carry on with the rest of the components same way. We need to rotate all these components, and we can keep the same size of the board as well for sake of practice. Of course, we can make the board much smaller comparing to the through-hole parts, but let's keep it the same size. But one thing we can notice here is that the designator size doesn't fit the component size. So now we have very small component, and the designator is really large. So we can make the designator smaller, and to do that, you just select it. You can click on properties, and you can go in here and change this one to 30 mil, which is half the size, and change the stroke to, let's say, 6, and now looks fit. Now it's good fit now in terms of size, but you don't have to do that for every single designator. Basically, you can select one, click on shift, and start selecting the rest. So this is the first method. You can go now to properties, and if you change the properties, it will apply on all. So this is one way to do it. But what is the other way is you select this component or this item, right click on it, and click on find similar objects. So now in find similar objects, now you can select all similar objects according to the specification defined in here. So we need only designator, so you select same. If you need something to be, we only need to select designator, so we need same. So it doesn't matter, they are all on the top overlay. So if you need only on the top, you can select same. If you need on the bottom, you can select the bottom in here. So what we care about is really now here, it's to select all the designator. Now if you click, for instance, component, because we right click on LED3, if you select same, so only LED3 designator will be selected. Now if you keep any, all the designator will be selected now. Now if you click, you need to have select matched in here. You need to activate this checkbox, and okay, now you can see all the designators are selected one time. So now you can go to the properties and you can edit the text height, change it to 30, and it will change for all. And we need stroke width to change to 6, and everything now is homogenized into the same size. So this is very handy, especially if you have very dense board with so many components, hundred and hundred of components, and you need to make a global change. So you can count on the find similar object and filter out the things you need or the elements you need to make a change, global change to these things. So this is one way. There are other ways to do it as well. So let's start by rotating all these LEDs. I'm gonna move fast now to try to finish the board layout very quick, and you can practice at your end. You can change the design from through hole bars into surface mount components and do the layout. So let's align. Remember, we can go to edit, align. Let's align them to the top, and let's make sure that the spacing between all these is correct. So distribute horizontally. Now they are all spaced. Same thing for resistors. Let's align them to the top, and let's make sure that they are spaced. It looks like they are spaced correctly, but it's distribute horizontally. Yeah. So what we can do now is we can move these designators or labels close to this LED. We can select all of them and we can move them one time. So these are good. So R1, R2. Okay, looks good. Let's do the other way. Also, these are rotated, so we can rotate these. Just select the component. Basically, I'm holding the components in here. So left click in the mouse, it will select the component. Space, it will rotate in place. Okay, let's do the rest. Usually after sometimes when you practice PCB design and you get the skills, you will start routing boards very fast, and you know what is the best way to position the components and how you can finish the board really fast. So let's make sure that these are aligned. It's okay. So this is the power. Now, why do we see an design rule error in here? Because the spacing between the pads for this surface mount components, it's much smaller than the design rules we set for the through hole bars. Now, when we covered the layout and schematic and the projects, all the parameters, design rules, electrical rules we set for the first project are still in there. So they have not yet changed. We still have these. Now, when it comes to surface mount components, the pitch between the two pins becomes much smaller, and the clearance between the two also becomes much smaller. So you need to specify the design rule according to the components you are using based on the spacing, the pitch of the component, and so on. We can change this in a bit. So let's move this coupling caps close to this. Designator can be moved in here, and this is Q3. I think Q3 belong here, and this one is closed. You see they are swapped, so this has to go in here and this has to go in here, and we can see that clearly, and we can flip this like that. Okay, can have them aligned, and then we can move this in here. Let's see what we can do. And R10 is in here. Let's see. So this goes in here. T1, R2. Okay. C3. T1. R3, R11. So when you move the components, you know the shortest trace, shortest route for it. Okay. Let's see. Okay. Okay. You don't have to worry about the designator now. You can adjust them later. And for myself, when I do design, what I do during the component placement and routing, I hide all the designators because really they have nothing to do with the placement and the routing. So what I do, select all the designators, same way I use for the filter, and I go in here and I click on this, and everything now is hidden. All the designators are hidden, so I don't have to worry about them. So I can adjust them later. Let's see. This is 5 volt, okay. And this is also goes to the 5 volt. Disconnect between the two. And I don't want to get the component very close, so let's keep some spacing for now. Usually when we have a really high density board, the components will be very tight in terms of spacing. So I think it's best to, if we move these components close to here, because they connect to the power switching transistor, so there is no point to keep them far away from this point. So 5 volt, and this goes in here, and I prefer to have this here. So this goes in here, this goes in here, and okay. Okay. This goes to 5 volt, 5 volt, and this goes here. Yeah. You might need to change the component position after you place them during the routing process. So and this is also very common. So you start with initial positioning, you start with planning as we talked in previous sessions, and then you start placing your component, and after that, if you find better placement for traces to better fit, so you change or move the components. Because one of the most important best practices is making the traces as short as possible. Don't go with long trace, go all over and move around the board to round 2 points. So try to find the shortest distance to route your board. Okay, so this goes in here. Just see if we can make this simpler. So this is 5 volt, and this goes, oh, this in here. Okay, we can put this here. And this one also, it's okay, we can put this in here. We can have this like that, and okay, this goes here, this here. Okay. Let's move this a little bit up. Have it like this. This can go here. So let's see if this connector is in the center of the board. So basically, as we learned before, you can go to report, measure distance, and we can click on this corner, go all the way to the center of this. So you have around 27.3 millimeter. So what you can do, you can take this all the way here, and you have around 29 point, almost 30 millimeter. So it's better to move this a little bit down. Okay, it looks good. As you can see, we can make the board way much smaller. Let's make it smaller so we can also practice this. So let's move these LEDs up. Up here, or if you hold shift down, so they will move vertically and you prevent them from moving horizontally. So shift down, so they will move vertically. Okay, this is good, just to practice how we can modify the board size. So we can move this also a little bit down. And this connector needs to be on the edge of the PCB in here. That's fine. And now we have the board outline from the old project, so we need to delete this one and create new one since we are going to change the board size. So click on any one of these lines and then click on tab, and everything will be selected. Everything connected to this line will be selected. Now delete, that's removed. Now we need to switch to the board planning mode so we can change or modify the board shape and board size. The only way to modify the board shape and board size is to go into the board planning mode. Now you go to design, edit board shape. Now we can left click and we can drag, and then okay, and maybe you can make it smaller. It looks good like that. Now we go back to view 2D mode. Now this is our board. We can squeeze these LEDs also and make it smaller from this side. Let's do it. So one way to do it is you can move everyone like that, but another way, if you go and change your grid. So in this case, you can use the arrows on your keyboard to move the components. How we can change the grid? One way is to click on free space in here, then the G key. So here you have the predefined grids in here. So the other way is to go basically to the properties, scroll down, you have grid manager in here. We talked about this. Go to the properties, and now let's change the grid into, let's say, 100 mil. And now okay. So you can see that the grid now is changed. So now at 100 mil, basically select all these. If you click on Control and left arrow on your keyboard, you see they are moving. So it's 2 steps. This is the fastest way to keep them aligned. 1, 2, and select these. 1, 2. It's just you are holding Control down. Now you don't have to hold Control down. Now you hold Control down and the left arrow. Then release the control, select the component, Control down, and they will be aligned. One more. Okay, now we need to change the board size again. So we go to the view, go to the board planning mode, design, edit board shape, resize the board size in here, and maybe we can make it smaller in here. And now you go back to the 2D mode. This is a good size. Of course, we can make it even half the size, half this size, but this is enough. It's just practice. So let's start routing. To start routing, I always prefer to hide the component overlay, the component overlay layer. So you only see the pads. Basically, these are the pads for the components, the surface mount pads, as you can see here. And the only holes you have here are the mechanical holes for fixing this surface mount connector, a micro USB connector. So let's hide this. Again, the shortcut for routing is Control W, and you will select that. But before we do that, let's go back to the grid, our grid 5mm. So if you click G on the keyboard, you go back to the 5mm, or the other way, if you go to the properties and you are on the free space, you click on the grid manager, you can select 5. Okay, and this is the grid. So shortcut, this is a quick shortcut for the predefined sizes of the grid. So now you can select the route from here, or you can select Ctrl W. Now when you click on this, you can see how the other pads are isolated. So if you want to try to come closer to this pad, you won't. So basically the trace is pushing the obstacles and hugging the obstacles. This is the mood now, the routing mood. And we will talk about these modes later, but now you cannot get closer to any trace or pad doesn't belong to the same net. And this is a nice feature in Altium Designer, because now you will get an idea about the clearances and spacing in this mode. Now Control W, you can hide this, or you can show this feature. Let's keep it on, it's very useful. First one, and this feature is called clearance boundaries. And again, remember, if you select a comment, you start a comment, and now if you click on Shift F1, you will see a list of all the shortcuts for this specific comment you are selecting right now. So let's take a look. Where is it? Control W, show clearance boundaries. So you can hide the clearance boundaries in here. Let's go back to the list, or show clearance boundaries. And this is a shortcut for them, and this is very handy. I use it all the time. So here you select. Now the second thing I wanna teach you today is the auto connect or auto route, interactive routing. And basically Altium will complete the routing for you. So if you start the routing now, if you hold Control down and left click on the mouse, everything will automatically selected or routed. So I'm not routing anything, I'm just holding Control down and left click on this net, and Altium Designer will try to find the best routing for this wire or this trace. So for instance, let's see this one. It's very quick, so we can route the board in fast. I'm holding Control down, left click on the mouse, and Altium Designer will route between two points belong to the same net. So this one. Now these are simple. Let's take a look at a much more complex like this one. So here, if we hold Control down and click on this trace, Altium Designer will try to route following the design rules specified under the design rules. So the spacing, the width of the trace, everything will be followed from the design rules. So you can adjust the routing after that. So let's complete the, so let's follow the same thing. So you can go with the traditional way, Control W, then move from the first point to the second point, or you can select Control, left click, and Altium will do that for you. This is interactive routing. We can route the board very fast. Let's see here. Okay. See this one and this one. Or now for these, since all these are on the same net, you don't have to route bad by bad. So basically go all the way to the last one, and they are now all of them are connected, as you can see. So you don't have to do one by one. So let's do this one here, and this one, this one, this one, that. Okay. And do this one. It's just control down, click, control down, click, and that. These are going to the 5 volt. Let's see, do that very fast. Okay, now here we have power supply trace, and we have another trace. This belongs to the switching circuit. Which one has a priority? Always when you have high-speed signals, they have a higher priority than other low-speed signals. Data buses have the highest priority. So if you have data bus with 8 bits, you need to route all these 8 traces together from point A to point B, and they have the highest priority. So if you have high-speed signals, they have the highest priority. Don't give the priority for low-speed or power supply signals to change the layer for these traces from layer to layer to allow another low speed signals to pass. So now I would give this one a priority to go, and because for power traces and the ground we can use vias and to go into power planes, as we will see later when we do multi-layer board design with power planes. So here we will see, we are going to use a VS for this 5 volt. We can route it from here. We have trace, but okay, let's see this. So if I click on now, hold control down and left click in the mouse, so Altium Designer will do auto routing for this trace. Yes, you still need to adjust the traces, fine tune them like that. So let's see. This one and this one. And this one goes in here. This one goes in here. So we can make this shorter like that. Ground. This one is connected here. But we are gonna have polygon for the ground, so that's fine. So we have 5 volt in here. We can take this all the way here, and also we have 5 volt in here. All the way down here. Okay. What left? We have one ground line, and we have this 5 volt. So this 5 volt, what we can do, let's do via for this, but be careful now. This is very important point here to watch out. So this is your source supply that will supply, basically your supply will come from the USB connector, micro USB connector, through this trace here, and from here your supply will distribute to the first set of the LED on the anode bin, and the second set of the LED on the anode pin as well. So basically all these LEDs are loaded into your power line at the same time. So when you distribute your power supply, you need to make the power supply traces thicker than the signal traces. And also this is one of the PCB design considerations we will talk about in one of the sessions in the future. So how you can calculate the current capacity of the trace. We can use the calculator in the Saturn PCB design toolkit. Let's run it. So we talked about this one in the first session. You can download this calculator. It's free, it's very handy, and it will help to calculate PCB trace current, and it's very helpful also via current. We'll use it later on. So but for now we can make these traces thicker, a little bit thicker, and we can try to route this. So let's route these traces. Power, let's find the best route for these. Here. So let's use a via. So in here we can select. Now you need to add a via. Click on the shortcut for this is the plus key on your keyboard. Once you click on the plus, a via will be added, but this via following the default rules set in your design rules. Let's see what design rules we have for the via. So design rules, we didn't use a via in the first project, but now we need to specify the via size. So the via size preferred always if you have low density PCB and you wanna have low cost PCB fabrication. So the diameter, make it 0.6 millimeter, and the hole size, make it 0.3 millimeter. This is a good size for low density PCB. So let's, even if it's in mil, you can write in millimeter, and Altium Designer will convert that into mil automatically, so you don't have to worry about this. So basically this is what you need. So if we delete this one now and let's start again, so you start, click plus, and this is now the via. Now once you click the via, Altium Designer will switch to the second active layer, as you can see in here. Now if you go all the way to this point, and if you stop at this, and if you click plus, and you will add a via, and now they are connected. And these are connected. If you hold Control down and double click on this trace, it will be highlighted, as you can see. Now these are connected together, and this is just an example. Now let's try to change the width of this trace. So let's say, what is width? It's 16. Let's change it to 20. So basically select a segment of it, tab, it will select all the connected on the same layer, then another tab will select everything. So go to the property and change this. Oh, because it select the vias right now. So let's select this piece, properties, 20 mil. Now everything now has changed to 20. Now let's select this and 20, and we have this as well, 20. Now the bar traces have thicker widths. Now here you need to be careful. It's bigger than the pad, so keep it at 16. Properties. We can solve this in the when we use regions for the power, and also this is something we'll talk about in the next two sessions. Okay, so for now I'm trying to build simple board in as fast as possible without any complications. I need the new engineers who are learning Altium or PCB design for the first time to enjoy it without adding complexity to it. Because even with this simple level, I'm receiving some comments from friends and students. They are saying, "Oh, this is very complex. This is very high level. No, this is very something. This is very simple." And I'm trying hard to simplify it as much as I can, just to make it fun for you so you can enjoy it at the beginning. Then we can add complexity to it step by step. I don't want to go complex from the first project, so this is the simplest project I can use as an example for you. So ground. So we still have this. This is the last wire we need to route, but you don't have to do it if you want to put polygon on the board, because the polygon will connect all the ground uh, paths together. So let's go and add polygon as we did in the last project. So polygon boards. So design place. Sorry, polygon board. Now hit before you place the polygon, you need to uh, set the properties for this polygon or the configuration. So you can place it and set this configuration later after you place it, or you can place it from now. So click on tab, and this will pause the command and will give you the options to change that. So we need to connect this polygon into the ground net, and also we need it to be on the top layer. You can specify a name, or you can activate the checkbox for auto naming. And again, keep these 500 square mil for removing islands less than in the area, and for the arcs it's half mil. And activate remove dead cover, and you need to have pour over all same net objects. Now we will talk about every single property of these later on, but now use it as it is, because it's long discussion if we want to go over these. So these are the properties I need. I need to make sure that I'm connecting with the ground, and I have it now on the top layer. Now once you are done, so basically either you click on this or you hit enter, and the command will be released. So you go to the corner, click in here, shift the space to change to 90-degree angle, change the mode to 90-degree angle, go all the way to the other corner, space again, so you move the direction, go all the way back to the corner where you started. Click on it, escape, and now it's released. So everything should be connected now to the ground, as you can see in here. So this one is connected. We had like flying trace in here not connected to the ground, which is this one, and now it's connected automatically because everything is ground and everything is connected to the ground. And now we have the ground on the top layer. So we have ground in here, it's also connected, and we will talk about the spacing between two surface mount paths. We can change that now in the rules. If we go to the clearance, and we have now surface mount paths to surface mount paths, let's set this to 6 mil, and it's enough. You can measure the distance actually between these two surface mount paths. If you select report, measure distance, and you need to change your resolution to 1 mil, and you can go all the way down here. So you have around 7 mils or 8 mils between these two paths. So Shift C, you can clear it. Let's add a polygon to the bottom layer. So you go here, select the bottom layer, again place, and you go to polygon board, tab. Now already automatically selected the ground, and you have it on the bottom layer. Let's start placing that. Go all the way to the corner where you started the first one. Can change the direction all the way to the other corner, and space, change the direction, and back to the corner where you started. Now right click, it will release the command, and you will get Looks like it didn't take the current. Let's see if we have ground. Now, how you can make sure if the ground is active or not? So let's remove the top layer. So we can see the ground bore in here, but it's not connected to the ground. So what is the reason for that? The reason for that is that we don't have any bad or hole connected to the ground on the bottom side of the board. Nothing at all. So there is nothing on ground on the bottom layer. We only have 5 volt. So how we can connect the two planes? So we don't have anything. We might not need even a ground on the bottom layer, but how we can connect the two together? So one thing we can do, we can add via stitching. This is something new. I prefer to talk about later because there is a reason for via stitching, which is reducing the current loops and improve signal integrity as well. So let's see what will happen if we add one via. So if you add a via, let's say copy this via and place this via somewhere on the polygon area here. And now if you go to tools, polygon board, you board all, and now you can see the ground on the top and bottom because now you have something to connect to. But if you remove this via, now this via connect the top layer and bottom layer. If you go to tools, polygon board, reboot all, it's gone. So now the polygon exists, but there is nothing to connect to it, so it's not built up on the board. Let's put the via back to the ground and tools, polygon board, reboot all, and now we have the ground. So instead of trying to connect the top and bottom, there is one nice feature in Altium. It's called via stitching. You can go to tools, via stitching and shielding, and we are going to use this more often in multi-layer boards later on. So add stitching to it, but this is very quick. Now if you click on load values from routing via style rules, this basically will go into the design rules and bring the via size for routing. So we need to select the net to be the ground in here, and here you can select either alternate rows or not alternate. So when you do alternate, basically they will stagger, as you can see in here. Just very quick off the shelf. So we have this via, and we had diameter 0.6 millimeter, and as I remember, and 0.3. And now you click on, you have the ground, click on OK. 182 stitching via added to the net ground. So if you click OK, these vias, not sure why they are not showing in here. Oh, they are. Oh, something is wrong. So let's just click on the see the rules. Oh, it's not millimeter, so something is wrong. It's 0.3 millimeters and 0.6 millimeter, not mil. So apply. Okay, and now this, as you can see, these are the GND VS. So you can reduce the size for these. Basically, if you select, once you click on any one, basically you are selecting the VS stitching group. And here, if you change your spacing between these into 200, click on apply, and now you have 31 stitching via added to the net ground, because now the spacing between center to center of the via is 200 mil, and we can measure that. So report, measure distance, so click on the center all the way to the center, and it's 200 mil. So as you can see, it's GND via stitching group 4. So shift C, you will deselect this. As you can see now, everything is routed and you have a solid ground. Now if there is a point where you can add a via manually, you can do that. So basically, you can copy any ground via of these, and you can add it in here. But make sure you are not adding the via where you have collision, or for instance here. If you add it here, you can see it's violate the clearance rules, and if you zoom in, you will see this distance from this via to this trace is less than 8 mil. So you will see real-time design rule check. So everything looks good. Now we need to add the outline for the PCB. If you recall, you go to design, board shape, create primitives from board shape. So, and keep out layer, it's 5 mil, always use this, click on OK. And now this one is very close to the edge. You need to go back to the tools, Polygon board, and reboot all, and the Polygon will push back to stay away from the outline of the board, which is what we need. And what is the distance between the Polygon board and this edge? It's defined in the rules. So if you go back, so you have poly, this is a poly, and you have trace is 12 mil. If you have anything else, these are the distances between the polygon and anything a trace or via. This will be considered as trace. And for some reason, okay, tools, polygon board, reboot all. Design, board shape, keep out layer, okay. Tools, polygon board, reboot all, okay. Looks like I deleted the stitching group by mistake, so we have it back. And now we need to go back and show the designator. Let's hide these cover layers and show the designators. And they are hidden. So how we can show them now for the designator? Basically, if you click on this, you can show the designator for Q1. Now, if you click on Q1, find similar objects, all the designator, same designator. Now they are selected. You go to the property, click on show, and here they are. Looks like we moved the components when they were hidden, and now we can go back and show the paths and traces and the components as well. We can show everything, and we need to adjust these. Is it possible to hide the polygon and keep only the traces so we can adjust these designators? Yes, you can go to Tools, Polygon Board, and you can click on Polygon Manager in here. Or you can right away click on Shelf 2 polygons. So Altium is telling you that you have 2 polygons and you can shelve them. By shelving them, you are hiding them. You can restore them back. And you can do that from here. And you can restore them by going to Tools, Polygon Board, Restore. And you need to board them again when you restore them. And there is a features in the preferences. We will activate that where Altium will auto pour the polygon every time you make a change. So the other way is to go to the polygon manager, and here you can see the polygons you have. So you have the first one, it's on the top layer, it's connected to the ground, and this is the second one, and on the bottom layer is connected to the ground as well. So if you click on shelf, these two are shelved right now. If you click on OK, and they are shelved. Now let's move these labels or designators, and to do that, in order not to move trace by mistake or move a component while you are moving a designator, click on the free space, go to the properties, deselect all objects in the filter and select only text. This is what we want to move. So this is the text, and this belongs to this component. As you can see, it's masked. So let's move all these together. Okay, can move them together. good. Can move this in here, and these resistors are, can put it underneath, but make sure you keep the distance. So if you get closer, you see the violation, how it tells you in here the spacing between the two text are smaller than 10 mil, which is defined in the rules as well. So if you have a text to other text smaller than 10 mil, so text to text silk screen. Okay, so it's called, this is considered as a silk screen, solder mask, silk screen. So silk screen to silk screen is less than 10 mil. Let's change this one to 1 mil. Minimum solder mask, also change it to 1 mil. Silk screen clearance, this is the silk screen clearance. So silk text to any silk object clearance is 1 mil. Now it's gone. You can make it smaller, but let's put it underneath the component here, here. As you can see, once we select the text, the corresponding component will be masked, as we can see in here. So this is the silk screen layer. Okay. Q1, let's rotate this one, put it like that. Let's hide the traces so we only see the components. Here D1, this is R10, where is R10? Okay, this is R10, C1, G1, Q4, let's put it on the same side as Q1. So R, as we can see here, we have, it's like we copied this, but we did not move it, so this is an error, as we can see. I will leave it so we can see how the DRC will show this. So this belongs to this. All these resistors, it's like they were moved. Okay. Here. Okay. Let's align these, edit, align to the top. They are all aligned right now. Let's move them in here. LEDs. So now these are left to right if you look bottom up, and these are in the other way. So better to have them just for how the board will look like. It's better to have them in the same direction. It's easier for the assembly as well. This will not make it confusing during the assembly. So let's just rotate these very quick. Select space and it will rotate. Keep it close to the component, and here we can align them. Let's align them to the bottom and bottom. They are aligned now. Okay. And here we have, okay, this is R12, this is R13, and here we have C3. Can put it like that next to it. C2 in here, and it looks good. We have error here, I can't see it, but let's leave it because we will see how the DRC will show this. So here you have the text which we placed on the top overlay. You can also place the text on the bottom overlay, and to do that you switch here to the bottom overlay, And let's hide everything on the top so you know you don't get confused between the top and the bottom. So let's hide everything on the top, and this is the bottom overlay. You can place anything anywhere in here. So let's place text on the bottom overlay and place it in here. But you need to mirror this because it's on the bottom side of the board. So be careful about it. When you place something on the text on the bottom, it has to be mirrored. So now you have text on the bottom and you have text on the top as well. We will see that. So let's switch to the 3D model. And here on the 3D, you can see we have the connector, we have the transistors, we have the oscillator circuit, we have the LEDs, and we have the current limiting resistors, and everything is connected. And here are the stitching vias. And these stitching vias, they look like, let me see if they are set to be filled with solder mask. So we need to clear the filter and properties, and they are tinted. So basically they will filled with solder mask. When you look at the board after it's finished, these vias will be covered by solder mask. You will not see them. And if you need to see the difference how they look, so if we select the groove in here, so now if we remove the tint, for some reason they are hidden. Okay, let's remove the tint for this. Unable to locate any. Oh, because of the bottom there is no traces. It's getting confused. Let's connect the shell to the ground. Let's ground the shell of the USB connector to the ground. Usually it's better to have capacitive isolation between the shell and the ground using 10 nanofarad 3 kilovolt rated cap in here. But it's okay, let's connect this to have something goes to the ground. So you need to update once you make any changes to the schematic, you need to commit that to the layout. So here it showed that G1 shell is connected to the ground, which is this shell. Execute, and if you go to the ground, you can see it's connected. Now all that you need to do is you go to the Polygon board and reboot all. You show and tools, Polygon board, reboot all. Oh, it's hidden, so we need to. Oh, now I know. So restore tools, Polygon board, reboot all, and it's connected right now. So let's go. Let's take a look at these vias. We'll fix this later, but I'm keeping this for now. Let's see the 3D model. Okay, so they are tinted. You barely can see those vias. So let's change these vias now into not tinted vias. Oh, for some reason, Altium Designer is removing these vias. But let's choose Polygon board. Let's put all. Let's add these vias back. I don't know what's wrong with Altium, so it's 0.3. Okay, let's import these values from Altium and template. This is the ground. Let's do 200 mil. And okay, so and these vias are tinted. Let's remove the tint from these vias. Okay, let's see. Now let's take tools, Polygon board, reboot all, F3. Let's take a look at the view 3D. Now, when they are not tinted, as you can see, you see the cover on the top and the bottom side of the via as well. This is a tinted via, and this is not tinted via, so you can see the cover. And there is no soldering or connection to the via at all. That's why it's preferred to have a tinting on the via. There is a debate, of course. Some people will say when you do high-speed digital design, and if you do a tinting, some moisture might go inside the via, and this will cause corrosion inside the via and will slow down the signal and stuff like that. This is very rare situation and never heard of, because um, there is a condition for these PCB operational condition and stuff like that. So tinting the via, in my opinion, is much better option. So I always go with via tinting. So let's change these to via tinting. So all of them are selected, tinted, apply. For some reason, Altium is removing the via. Let's add the vias again, stitching again. Ground, okay. Tools. Oh, Polygon board. You go all tools. Via stitching. Okay, tools, Polygon board, you go all. Now, the way how the via connect to the ground polygon or the port, as we can see, we can see this four corners connection. We can change that in the design rules. If you go to the design rules, you have plane connect and it's relief connect. Basically, relief connect, it's important when you connect two parts, not vias. So you can change that by going to advanced. So this is for bad connections. If you are connecting with a bad component bad, it's better to have thermal relief, because if you want to solder and desolder the component in the prototype, it's much easier. If you don't have the thermal relief, imagine that the bed is connected to this thermal or to this ground plane. You need to heat up the bed at very high temperature in order to solder or desolder. But for the via, nothing is connected to the via. Nothing has to be soldered or desoldered is connected to the via. That's why always, if you have a via connection, make it as direct connect. For the bad, make relief if you are doing prototype. When you do go for production and your prototype is finalized, you can go with direct connect. Direct connect is always better in terms of power distribution and signal integrity and impedance as well. So let's do this. Tools, Polygon board, you need to reboot all. And via, let's design. Did we change that? Oh yes. Polygon connect style, we change the power plane. We don't have power plane. We need to do that for the Polygon connect style. Via connection is direct connect. Okay. Now tools, Polygon board, reboot all. It's directly connected now. So what we need to do now, let's show the components layer on the top and bottom. Everything looks good. Let's run the DRC. Tools, design rule check, run design rule check. No errors. This is perfect. So this is simple board because this is really a simple board. But let's, for instance, move this designator over the bed. Now let's run the design rules. Sorry, tools, design rules. So now we have an error. Let's close this. If you look at the message, you have select to solder mask clearance constraint. So we have a collision. So if you click on it, it will show you that the spacing is less than 1 mil and you need to move your designator away from the bed. Now if you tool, reset error markers, it's reset now. Now you can go and design rule check and check it again and it's 0 error. Now the board is basically is ready, and that's all you need to do. Your board is ready for fabrication actually, and this is what you see on the top layer and bottom layer. And if you want to see whatever on the top only, you can remove the component. This is the top layer cover, and this is the bottom layer cover, and this is the component on the top layer. If we remove this, this is basically the silk screen you will see in the top, and this is the silk screen you will see on the bottom. You only have text, customized text on the bottom. If you really don't need it, it's better not to have it because you will save the cost. If you don't have a silk screen on both layers, this is cost saving. So basically this is solder. This is the solder paste location, and yeah, this is the solder pads and this is the solder paste. So when you do stencil printer, they count on the solder paste to laser cut the stencil printer. So this is the top. Yeah, so let's take a look at the 3D model. If we go to view 3D, and here we can see this is the top. We can view the board from the top, and this is from the bottom. And let's take a look at, you can go into view configuration, view options, and now you can space these ports. So you can see how these vias internally connect between the top layer. So you see here are the traces. This is the cover layer. And here are the vias goes from the top all the way to the bottom, and on the bottom we only have the ground plane. And this green one is basically the solder mask. And this gray one in here is the core of the board. This one in gray is basically the laminate material. And this is the 1 ounce cover, and this is a 1 ounce cover as well on the top and bottom. So now they are scaled, they are spaced actually. So if you go back to the original scale, now the thickness is 1.6 millimeter. And one thing you can play with right now, if you go to the configuration, now you can change the make the core a little bit transparent. So the core already transparent. You can make the cover transparent, so you can see the core, you can see through the core. So this is the cover. We can change, you cannot change top screen. You can make it transparent, and the core is already transparent, as we can see in here. You can see through it. So you can control that in here. So this transparent is not transparent. You can control that in here. Yeah, you can see the cover without the component also by hiding the component in here. Show 3D bodies. So this is only the cover. Control F will flip the board. If you click on Control F, you will flip the board. And let's show the component. So this is orthogonal view, and this is perspective view. This is 3D. Orthographic, it's basically you are looking from the top down view on the board. And perspective, you have the 3D dimension effect. And you can play with these settings. So the board basically is ready. And now the only thing left is to generate the fabrication files. So to generate the fabrication files, we need to create output job file. So let me do this from the beginning. We did it last time, but let's do it again. So you click on add new to the project, you click on output job file, and in the output job file, the first thing we need to generate is the fabrication files. You go into under as fabrication outputs, you click on the Gerber files and PCB document. Then you go to NC drill files, PCB document. Now you need to configure these files. You go into configurations. What are the layers you are using? So millimeter, if you're sending this to China, use millimeter. If you're fabricating these boards in United States, use inch. So keep this format 4:4. You go to the layer, you have a top overlay, top base, top solder, top layer. So basically this is the cover layer. So then you have the bottom, and also you have the keep out where you have the outline of your board. That's all you need to do. Okay, it's configured. NC drill file, you go to configuration again, millimeter, and that's all you need to do. It's done. You click on the container in here, folder structure, and you click on this and that. and basically folders will be created where your project is, and the Gerber files and NCDrill files will be positioned in that folder. Now also, if you want to do automated assembly, you need to generate a pick and place file. Basically, the pick and place file, if you go to the configurations, so they have the coordinations of every single component on board in X and Y, in addition to the orientation of that component. So here you can see the center of the component X and Y, where it should be positions, and the rotation of this component. Why rotation matter? Because the polarity and pin number 1 for the integrated circuits or the ICs, that's why you need the polarity. And here you can see the designator. So as you saw in session number 1, where a pick and place machine or robot arm will pick up the component from the component rail and move it to the PCB in its position and place it on the solder paste before it goes into the reflow oven for soldering. So how this pick and place machine works is basically read this coordinations from this file, which is called mounting file or placement file. And here you can see the coordination for every single component on the board, in addition to the rotation with some specific information, and whether this component is positioned on the top layer or the bottom layer. We don't have any component on the bottom, that's why you see all of them are on the top, and you can filter that. So this is only the top layer. So now you can generate that as CSV file, and you can use metric or imperial, and click OK. It's ready. Now you can add it to the container. Now a new folder will be created to generate the pick and place file for the pick and place machine. Now you need also the document for this file, so you can add the schematic. One of the things, you can add schematic print. So let's add this, and this goes into the PDF container. And you can also add a 3D model, PCB PDF 3D. Also this goes in here. And also what we can add document output. We can add in the assembly here. We can generate assembly drawing, and let's configure the assembly drawing. Configure, and what we need top overlay, bottom overlay, and mechanical. We don't need these mechanical layers, but we need the keep out because it has the outline of the board, and we can delete these, they are not important. Same case in here, we need keep out, and we can delete these, and that's all we need. On the bottom layer, the components has to be mirrored because they are on the bottom. So when they are printed, you will see them in the correct on the correct side. So okay, so let's configure the printing for this. We need a color to be printed in the color, and same thing for the schematic print. Page setup, select color, and PDF 3D. It doesn't need to be selected. Okay. Anything we can add in here? Let's save this file first. And this is under the assembly, job saved. Oh, one thing we forgot to add is the bill of material. Let's go to the report, bill of material, and add active bill of material document. So this is active. Let's save all. And now we don't have active bill of material. We need to add bill of material, active bill of material here. And this is very important things we forgot to add. Let's wait, it will come up in a second. So basically, the active bill of material, whenever you make a change to the schematic and change a component or add a component, it will automatically update. Now let's click on refresh. It's refreshed. As you can see now, this is the name of the component, and this is the designator. So these are the designators, and we have a description in here and the quantity of each item. So basically we have three 220 nanofarad caps. If you click on it, you can come here down here. So this is the primary selected components, and here you have alternative components, and these are the providers. The green one is the best option, and the one that is selected has priority 1. So if you go to the status manufacturing life cycle of this component, it's in production. Sometimes you will see obsolete, sometimes you see end of life. So obsolete will go maybe gray or orange. End of life will go red. So the sublayer, you can see DigiKey Mouser. So I want to select this component from DigiKey. I don't want to source my component from multiple providers. So what you can do, you can go here. Mouser is priority 1, DigiKey is priority 2. I can set this priority 1. Now it's DigiKey. Same thing for this. Let's have it from DigiKey. This one is from, let's have it from DigiKey. And this one as well. Here. Light electronics, we have it from DigiKey. Future electronics, have this from DigiKey. We can change that all one time in the component manager as well. And here you can see the supply unit price. This is the unit price, and this is the subtotal. Basically you multiply this by the quantity in here. So this is the total, and now you have information about the board cost right away. You can calculate how much component will how much the component will cost you actually. So, and this is very, very important. So let's save all that. So you need to save the bill of material as well. Now we are ready to generate the output job files. So let's go back to the output job files in here, and let's add the bill of material to the folder structure container. If you have a multi-layer PCB, more than 2 layers, you can maybe add a report for the board stack in here. Maybe we can add a drill drawing as well. Let's add drill drawing in here, and this drill drawing base setup. Let's see what we can add. Make it color and configurations. It's a drill. I need keep out layer on the top. Let's see what we have. A drill on the bottom. Keep out layer, and we don't need these layers. Delete for now. Delete. Okay, and save it. And this can be added into assembly drawings. We can add it here. So yeah, it looks good right now. Let's generate these files. Let's save all. Now to generate the PDF, let's start with the folder structure. Let's create that, and this file will be generated. The assembly pick and place. I think they are done. Let's close these. It's still generating. Let's wait. Okay, so let's close this file, and also, so this is the bill of material. Let's close it. Let's generate the PDF. So the first sheet will be the schematic print, and the second will be the 3D model, the third will be the drill drawing, and the fourth will be the assembly drawing. So now we can go to the project folder and see all these files. We can view them. Here's the project folder. This is the assembly, and for the history, this is just track of the history. You can go back to earlier revision. So, but let's delete this folder. We don't need it because it has a large size. You can reduce how often you create a backup. basically it will include the backup. Previews is basically preview for the sheets as we talked about earlier. And this is the logs, so it's basically a log of all the tasks you completed in the design. If you change anything, add net or change anything, this is a log of all the task you completed. Also, we don't need this, we can delete this one. So this is a project output. So here is the bill of material that was generated, as you can see, and we use a default template. We did not use any customized template or fancy templates. Basically, you have the name, description, designator, quantity, manufacturer, and manufacturer part number, the life cycle, supplier, supplier part number, and the unit price. Basically, in order to order this component, you go to DGKey, put this part number, and you will find the component. Or you can import these into as an Excel sheet into DGKey, and DGKey will form like a cart based on the bill of material for you. So we'll see how we can do that. So this is for the bill of material. So gearable files, these are the gearable files in here. So as you can see in here, so the first one, this is a gearboard file for the bottom layer, and this is a cover. Basically, this is the bottom overlay, and this is the bottom solder mask or the base solder paste, and this is solder mask for the bottom. Now this is the keep out layer. Now everything with T is the top layer. So this is the cover, this is the overlay, or basically the silk screen. This is the solder paste, and this is the solder mask. So these are the files. These are basically error report and rules and stuff like that. They are not important for the fabrication. These are the files that are important for the fabrication. You have 9 files, so you can delete these. You don't have to worry about this. And for the NC drill, it's basically the file you care about is these. So you have a rounded hole and you have a slot hole. So remember that the USB connector has a slot hole, not round hole. Most of the USB connectors have slot holes, and they have separate files in here. So the round holes, if you open this one or edit it, so this is basically the drilling for these holes. And if you need information about these holes, you can see them in this one. So you have 4 different type of holes. 0.3 millimeter, these are the vias, they are rounded, and you have 0.5 millimeter and 0.85 millimeter, these are slots, and also you have 0.8 millimeter, this is a round. So these are basically the holes you have on the boards. That's it. And for 0.3 millimeter, you have 34 hole, and these are the vias, as mentioned. And these are plated holes, and you have 2 non-plated holes. Non-plated meaning there is no cover going through the walls of these vias. So basically mechanical holes without any plating. So basically all that you need to send are these 2 files. So how these will look like when we upload them or verify them, we'll see that. So pick and place machine. So this is the pick and place machine that has the coordination for the pick and place machine. So here you can see you have R22. Basically you have the designator, comment, layer, footprint. This is the footprint. The center X, the location of the component, given that it's coordinated from the center Y, so X and Y coordination, the rotation degree, and if you have any description. So this is the file that pick and place machine will understand and read to position all the components on the board. Here you have the design rule check errors, and this is a report, just a report, and this is a status report as well. So nothing, file generated and how many files were generated, etc. And this is the file we viewed. This is basically you don't have any errors, you have traceability of this, and you can see if you have any errors generated. Just for traceability, you will have it all the time, and it's good to keep it, so you make sure that when you generated the file for this project there was no errors and it's ready to fabricate. So let's take a look how we can view these Gerber files before we send them to the fabrication factory or company, just to make sure that we generated the files correctly. You can check these files using the Gerber software we talked about in session number 1, Gerber View for instance. And in Gerber View you go to File, you can load Gerber files, and here all files. Let's go to the directory where we have this Gerber files. In here you can copy this in here, and you can select all of them. It's okay. So basically here are the files without the drills. So here you can copy and view each one of these layers, and you can see how they overlay together. This is the cover, for instance. These are the holes, bottom layer, bottom cover. This is one way. So you can use Gerber Viewer to view that. This is one way. So the other way, you can go to PCB way, Gerber files viewer, and you can drag and drop your files into here. So let's do that. Let's try that. So let's bring the NC drill files into that folder as well. We can copy these files and Gerbers, and here data trail files. Okay, just drag and drop. And this is nice actually. So you can see that the cover on the top, solder mask, cell screen, solder paste, and here you can see also this is Gerber view. This is nice. So this is the bottom, this is the top. Oh, basically they are here. So here are the layers, and now you can, if they are in the 3D model, you cannot change. So this is customized view. Top, this is what you see on the top, this is what you see on the bottom. So I think if you zoom out, you will see the whole board. They have problem with the scale. So the layers, here are the layers. Now you can hide everything on the bottom, and you can see, for instance, the cover on the top. These are the drills. So you can show these are the drills for the vias, and these are the slot drills, and this is the outline of the board. And on the bottom you don't have solder paste because you don't have any components. That's why you don't need this layer. So let's take a look. Solder mask on the top is solder mask, and this is a silk screen or top overlay, and this is solder paste. And cover, this is the cover on the bottom, and this is the solder mask. On the bottom we only have the holes for the micro USB connector. Silk screen, we only have this text here on the silk screen, and we don't have any solder paste because we don't have any surface mount component. Only when you have surface mount component you have solder paste. And again, basically the solder paste is a layer used to prepare the stencil for the stencil printer, which is made by the laser, so laser machine. So yeah, it's nice. This is another way to view it. There are a lot of Gerber viewers online for free. You can use them. So it looks good. Now your files are ready. You can only zip these files and send them to the fabrication house or fabrication company, and they will do the PCB for you. If you need them to assemble the board for you, you need to send them the pick and place machine in addition to the bill of material. And here we can take a look at very quick example. Let's say in here, so if I do PCB way, for instance, so you need an instance code for PCB. So let's say we need to make 10, and the size of the board is 50 millimeter by 50 millimeter. And okay, this is one, sorry, this is different design in pattern. We have only one design and single pieces, and we need 10 pieces, and it's 2-layer PCB. We need to do FR4, and the thickness of the board is a standard 1.6 millimeter. The minimum track spacing is 6 mil. We set it in our routing into 12 mil, so we know that it's 6 mil. If you go down to 3 or 4, it will be more expensive, and we saw that in the last session. And the minimum hole size is the vias 0.3 millimeter. If you go down to smaller hole size, it will become more expensive. Solder mask, let's do it green. You can select any color you want. Silk screen, white. I prefer always white. Gold finger. We don't need a gold finger, and we can discuss this later. So we need lead-free HASL. Also, we talked about this surface, different surface finishing technologies. So this is cheap, and this is safe. We can get lead-free. And tinting vias, yes, we need tinting vias, as we saw. Basically, the solder mask will be go over the vias to cover them, and it's a standard 1 ounce cover. So this is the finished cover. See, you can go all the way over to 13 ounce cover. This is very thick. This is interesting. So if you have any special requirement, you can write it in here. If you have something special in here, for instance, if you need to do impedance control, if you are designing transmission lines on the PCB, you need to do impedance control. If you need UL marking, so basically you are certifying your board by UL, so you need to add UL marking on the board. You can specify where do you need it, and etc. If you need any extra requests, you can do that. So SMD stencil, if you want to do the assembly by yourself, basically you can select SMD stencil, and here it will come with a frame. Better to order it with a frame. So SMD stencil, let me show you an example. This is the SMD stencil. Basically these are the SMD stencil, like that. They are laser drilled. Basically these are very fine, and this comes with a frame, and you need to put this on the solder based printer or stencil printer, like that, so that it will come over the PCB like that. You put the solder and you use squeegee like this, so you have squeegee and it go all over, and put the solder on the solder pads only. So this is a stencil. You can order a stencil if you have pick and place machine. I have a pick and place machine in the lab. Usually I order the stencil for $15. If you don't have this, you can go with assembly service. Basically, Trunky Solution, they will source the parts for you, do the assembly. And Kilido Consignee, they will send you a kit, and you need to order the parts, label them with the kit, and ship them the parts. Combo, some of the parts you need to provide by yourself, and the rest they can order for you, because some of the parts are unique and hard to find or customize, etc. So you need to supply them to the assembly house, and they can supply the rest parts that are common, like resistor and capacitor and so on. So board type, if you have the component on assembly side on top or bottom or both sides. Board type, if they are single pieces, like every board it's separate, or they are panelized, basically paneled PCB. Let me show you an example. Panelized PCB, like that. So all these boards are the same, but they are panelized, which make it easy and cost effective for fabrication and assembly as well. So usually they come as panelized. This is Altium image as well. So this is how you panelize a board in PCB. So you need to have these brackets between these boards, so you can crack them and separate these boards. So we can also talk how we can do that in one of the sessions if we had enough time for that. And here you can just specify the quantities you have, what are the number of unique parts. Basically, unique parts, how many lines you have in your bill of material. So you might have only 10 unique parts. One of the parts you use 100 piece 10 nanofarad cap. So this is just one unique part, even if you are using 100. And here you can specify how many you are using, etc. Then you calculate how much it costs, including shipping, and once you add it to the cart, they will ask you to upload the Gerber files and the assembly files, etc. So that's all for the boards. and for the fabrication files, and for the drawings, schematics, 3D model, assembly files, and assembly drawings are created in the PDF file. So that's all for today for this session. Next session we'll go into much more complex topics, and what you can do for as a homework, you can try to stagger these LEDs. Basically, you have one red on the side, then green, red, green, red, green, red, green, and red, and on the other side also you have green, red. So basically, just move LED 2, 4, 6, and 8, move them and replace them with, not replace them, move them in place of LED 11, 13, 15, 17, which you need to move them to the other side. So you will have red, green in a stagger positioning or format. Without changing the schematic, of course, and try to route the board. In this case, you will need to use vias, and the board will become a little bit more complex, just a little bit, because you can solve that with the via. You have two-layer PCB. So this is the homework. Try to do that, and you will learn a lot out of it. And one thing you notice in here, so when you click on the output job file, you can see the generated files. See, so here you can see the design rule check, the bill of material. It's all under the same project, and now you can view them from here. And these are the Gerber files actually, and you can view them in Altium Designer. So this is basically the bottom layer solder, and this is the top layer solder, and this is you see the bottom layer overlay, bottom layer solder base, but we don't have solder base, solder mask on the bottom layer. Let's see, we have, this is the outline, and this is top solder, this is the overlay on the top layer, this is the top layer paste, and this is the top layer solder mask. You can see them all, and this is one way to view also the Gerber files. So also you can see the NC drill files. You can take a look at the NC drill files as well in Altium Designer. These are the drills in here. And we have the pick and place file. We have it. We have the components that use on the board. And this is C. You have C1, C2, C3. If you click on it, it will take you to the schematic. You'll see the designator. And these are the nets generated in Altium Designer. The 5-volt nets. These are the 5-volt nets, and here we have the ground. We have net C2_1, meaning this net connected to capacitor C2, the pin number 1 of the capacitor. So this is the name of the net, and so on. So that's enough for our session today. Thank you